Hi guys, in this video we're going to go over two pumping theorem proofs, but what we're going to do is before each one we're going to use the closure properties for context-free languages to make to restrict down to a simpler language that we can prove. And I'm also not going to have time to go over a full pumping theorem proof for both languages, so I'm going to cover the important things like what string to pick, what cases you need to consider, and maybe how you would pump out for that particular case. So to get value out of this video, you're going to need to know the pumping theorem for context-free languages, which we've gone over in previous videos. We even have a full worked example. You're also going to need to know the basic closure properties of the set of all context-free languages. So things like the context-free languages are closed under union with other context-free languages, or if I take a context-free language and I intersect it with a regular language, the result is guaranteed to be context-free. So to dive straight in, the first language that we care about here is the language where every string can be broken up into two parts so that the first part matches the second part in order. So it looks a little bit like the palindromes language, except we don't have the reversal up here that we expect from the palindromes. So once we have a language in this form, we know that it's not context-free. So we can prove this one, but it's actually easier to start by restricting it down to a simpler one using the similar sort of closure properties that we did for the regular languages. So the closure property that we're going to use in this case is to intersect with a regular language. And what we usually do when we're doing this is we intersect with some sort of regex, which can give us some order properties, so that when we're doing our pumping theorem proof, we can rely on those order properties to make it easier to pump out of the language. So in this case, we've got A's and B's, and it would be nice if we could get down to something that looked like AN, BN, AN, BN. So what we do is we intersect with this language, WW, with the regular language, made by the regex A star, B star, A star, B star. Now in this case, we won't have exactly AN, BN, AN, BN. What we'll actually have is M here and here. What those closure properties have done is shown us that when we can prove this new language L prime is not context-free, we'll know that because the regex we intersected the original language L with was regular, that the original language could not have been context-free. So it's sort of a proof by contradiction within a proof by contradiction, because we're going to prove by contradiction that L prime is not context-free, and thus prove by contradiction that our original language L was not context-free. So this is a little bit like the AN-BN proof, but we remember that the number of B's do not need to match the number of A's, just the other number of B's. So what we can do is pick the string AK, BK, AK, BK and pump, but we need to keep in mind that we can't rely on having a different number of A's and B's to get us out of the language. We need to just pair B's with B's and A's with A's. And the simple intuition for why we can do this in all cases is that no matter which way the string UV, X, Y, Z gets propped up, because V, X, Y must be less than or equal to K characters, there's no way for us to be sitting in one region and to be sitting in the other paired region that we need to keep the same size. So whenever we pump out, we'll always be reducing, say, region 1 and unable to reduce region 3. And that's why we'll be able to pump out of the language. But we do need to look at all the cases, so let's look at these and then figure out which ones we need to worry about. So we have the cases where V or Y cross one of the regions. So either V or Y is sitting there or there or there. Now in each of the cases we can just simply pump out, and obviously we're going to pump out both something in two adjacent regions, but remember that we would need to change the two regions over here simultaneously in order to have the same number of A's as A's and B's as B's. So the crossing regions case is pretty simple. We can also pump in, and that would be even simpler because we'd have something that would match A plus, B plus, A plus, B plus, A plus, B plus, which doesn't match our original language. The other possibilities are that they're both in the same region, So we have this one, this one, this one, and this one. And they are obviously the simplest cases that we can consider because we only have to worry about modifying one particular region. We also have the cases where v and y are in adjacent regions, such as 1 and 2 at the same time, or 2 and 3 at the same time, etc. Finally, you can see that we might have to worry about the cases where v is in, say, region 1 and y is in region 3, v is in region 1 and y is in region 4, or v is in region 2 and y is in region 4. And if we covered all of these cases, we would have every possible way of putting any v or y in there. However, remember that our constraint here, that the distance between the first symbol in v and the last symbol in y has to be k or less, that these three cases here are impossible. And it's the fact that those cases are impossible which lets us pump out, because we wouldn't actually be able to easily pump out in these cases. So we're going to look at a very similar language, still the language where the start and end have to match in order, but this time we're going to look at a slightly larger alphabet where we include a third symbol. In this case, we're also going to use intersection with a regex, but we're going to use a slightly different regex. And we'll end up with a slightly different pumping theorem proof. So that way you can see a few different examples. In this case, what we want to do is, again, give ourselves a start and an end bit that's definite. Because if you recall when we've tried to prove this language not context-free in the past, one of the key problems is if we chop stuff out of the middle, we don't necessarily have what we might have thought as the start and end, because the middle of the string may have shifted. But if we use a regex cleverly here, we can set up what has to definitely be a middle section of the string. Now the regex that we're going to use to do this is the regex A union B clean, C, A union B clean again, C. What we end up with as a result of intersecting WW with this regex is the language of strings of the form WC, WC, such that W is some string made up of just A's and B's. Now we can see that this still fits the format previously, where we've got the front half of the string matches the back half of the string, and they must obviously be of even length. But in this case, what we've introduced is definite position markers here in the forms of individual C's that can't be anywhere. And then we have these strings that have to match W, where these are only made of A's and B's and maybe of any length. What we know is that because we have represented this using a regex, it must be regular. And we know that if we intersect a context-free language with a regular language, the result must be context-free. So that means that if the resulting language here, which we'll call WC, if WC is not context-free, then we know that either this regex or WW weren't in the memberships that we assumed. But we know that the regex is a regular language, since by definition anything that we can represent using a regular expression is a regular language. So the only possible conclusion from proving that WC is not context-free is that WW is not context-free. And we will prove the former in the next slide. So now we have to prove that this language where we have a WCW, so we have a C in the middle of the string and the bit before the C has to match the bit after the C. Now, in the last pumping theorem proof that we just did, we had a format like this. We don't have that guaranteed format anymore. We don't have to have a certain number of A's and B's, and we don't have to have any order to the A's and B's when we do this. So we can't rely on order, because this time we've only constrained that the start and the end match. But we do have the nice simple fact that there always has to be a single C in between those two matching strings. And that's where we will end up simplifying our cases. So we're going to choose the string AK, BK, so similar to our string before, C, AK, BK. And as always with our regular language pumping theorems and our context-free language pumping theorems, we always specify them with respect to some undefined integer k. That's because we have to fight against an adversary of sorts that's picking strings as long as they want them to be. So we define them with respect to some k, and then later when we go back and look at the pumping theorem which says there exists some k such that blah, we will show that because we said for any k, we've proven this to be false. So our first case is V or Y touching this middle region here, V or Y containing the C. The reason this one's the easiest case to consider is we simply pump out. If V or Y have that C in them and we remove it, our string will no longer contain a C and will obviously not match the language format that we have up here, which required exactly one C. So if V or Y contain region 3, we simply pump out and obviously the string is not in the language. Now we are going to use the C to mark the middle of our string, and we're going to call the regions 1 and 2 the left and regions 4 and 5 the right. Now another option as well as having V or Y overlapping the region is to have them both on one side or the other. So if we consider the idea that V and Y are both over in region 1, 2. No matter where they are in that region, they have to together be non-empty. That's what this constraint here says. Because they have to be non-empty, if we pump out, we will end up with something over here that has less than 2k characters. So trivially, we don't even need to worry about what it is. It cannot match something that has 2k characters, as the right-hand side still does, because we had nothing in the right-hand side. And you can see how we could do the exact same reasoning if V and Y were both contained over on the right-hand side. We simply pump out, and no matter what, we're going to end up with a section on the right that's not long enough to match the section on the left. So that section there is actually quite simple as well. And the final case we actually have to consider is that V is in region 2 and Y is in region 3, but we don't contain region 3, because remember we can have this X in the middle here which can be non-empty. So in theory we could have V sitting in region 2 and Y sitting in region 3. Now all we do is pump out again, and we're going to have something A, K, B, Q with an integer less than K, C, A, Q, B, K. And they obviously don't match unless Q equals K, but because V and Y were both in region 2 and 4, they're therefore obviously not empty, otherwise that would have fit into our previous case. So we know that we're going to have something that doesn't match. Now, you might also think of some other possibilities, such as V in region 2 and Y in region 5. The reason we know that's not the case is because of our usual constraint on length. So we have Vxy has to be less than or equal to k characters long. The only way to have something in this region and something in this region is to have something that spans larger than this region here that is of length k. That's one of the reasons why we usually pick regions to be of length k, because we know that our section that we're pumping has to fit into one block of k characters. So we obviously can't have something on either side of a region that is k characters long. So for the same reason, we don't have to worry about the case where V is in 1 and Y is in 4, or where V is in 1 and Y is in 5. And we don't explicitly handle the cases where something's overlapping here, because we already considered the possibility of V and Y being in both entirely in this region and entirely in this region without worrying about where they were. And we obviously don't have to worry about V or Y overlapping this section here and simultaneously sitting over here, because that would require it to be longer than k characters. So this isn't a video where I've taught you a concept, so there's not going to be a summary slide like normal, but what I hope you did get from this is a little bit of an idea on how to use regular expressions and the fact that the context-free languages are closed under intersection with the regular languages to enforce some order constraints to make our context-free bumping theorems less abstract and more formulaic, so they're simpler to do. And also how to do some of the core components of a context-free bumping theorem proof, like picking the string and deciding which cases you do and do not have to consider, and then how to reason at a slightly more abstract level so you don't have to specify too much detail when you're going through the context-free pumping theorem proof. So these two examples weren't full worked examples where I wrote everything down because that would have taken way too long, but hopefully you've got a little bit of an idea on how to more easily do some pumping theorem proofs.